this computer. Okay. So we are continuing with that. We are continuing with this, right? So I said that, yeah, there's another comment in here. So this formula is correct. This is correct. Don't add additional units. This is one type of mistake, right? But there's another type. So this is the formula, right? mg. And we know that g is equal to 9.8 kilometers per second squared, right? So as a result, some people, instead of writing this formula, they just think that they serve a, I don't know, they do something good if they replace the value of the gravity with 9.8. So therefore, they write down this formula like this. Again, this is wrong. So let me actually do it like this with a red color. This is wrong. This is actually dimensionally incorrect. Okay. The reason is that if you just look at the units, the right-hand side has the units of kilograms, but the left-hand side has the units of newtons. Okay, and so as a result, you cannot. It's not possible that something with a unit of force can be equal to something with the unit of kilograms, right? I mean, there's something wrong in here. So if I insert 100 kilograms in here, perhaps I can get this, but I don't know. If I use, for example, let's say 100,000 grams, what do I get then? Okay, so there's something wrong in here. So therefore, this is an incorrect formula. If you want to do this, do it like that. I mean, that's the correct way of doing it. Do not write down the numerical value of this. Write down the numerical value together with the unit. So the correct way of doing this is basically writing this. It is 9.8 meters per second squared times Sm. Okay, so that's correct. Okay, this is wrong because we don't have these. You haven't written down the unit that comes with this quantity in here. You have to also insert the units there. In that case, that would be a correct expression. Okay, so as a result, I mean, both of these, this one and that one, they are both correct. But there's a problem with this. I mean, there are many problems with this. Let me say it like this. Problems. The first problem is it is hard to read. Okay. I mean, the more things you write down, it becomes harder to understand. So a simple formula like that, a simple formula like this one is actually easier to understand. Okay. The second thing is that, well, not valid everywhere. Meaning that the G in here is a gravity, even though on the Earth it is constant, more or less. It doesn't have the same value, for example, on the moon. So it is a different value on the moon. So I know that this formula is valid on the moon and on the Earth and space and whatever. Wherever I go, this is going to be valid, but this is only valid on the Earth. And so basically when you are writing this numerical value, you're somehow taking a very general formula and constraining it to a very small place, right? So it has less applicability, right? Hard to read. It is only valid for some small situations. And what else? Yeah, this is more or less like that, right? Sometimes, I mean, if the formula, these coefficients are too complicated, but somehow they add up to some certain constant numerical value, especially astrophysicists actually use these kind of things. So I don't know, for example, the power emitted by a star, for example, they actually express it, for example, in terms of mass divided by the mass of the sun multiplied with, I don't know, 10 to the 20 watts or something like that. They can use these. This is just a formula that I just invented. I don't know what the relationship is, so I think that power depends on temperature as well. But in any case, sometimes astrophysicists actually use things like that, especially when the formula is actually quite complicated. So in that case, I mean, this is easier to read than the actual formula. So yeah, you can then use these kind of expressions. No problem with this, all right? But usually, I mean, especially for the problems that you're going to be interested in your must courses, it's usually the case that this is more complicated than the actual formula. And of course, the last thing is, it's just a repetition of this. It's easier to read. I mean, there's a magic number in here, and it's hard to understand what it is. But if you have been using G for a certain concept for a long time, let's say, then by just looking at that expression, it's easier to understand what it is saying than this one, okay? So as a result, if you don't have to, do not use this kind of an expression, just use the old formulas with everything is expressed symbolically, okay? Just keep this in mind because this is kind of better for us, okay? So that's the last comment about that. Okay, so that's about the units. So the units are necessary. We always have the units, write down the units. There's some kind of an exception that I sometimes do. I mean, if I do some kind of a derivation, right? I have some kind of a formula, for example, I don't know, mg. Instead of writing down the units in here, I just do the calculation because the calculation might be actually quite long, and then write down the units in here. So as a result, at intermediate steps, let's say it like this, you can forget about writing down the units because it takes too much time and makes the expression complicated. Even though mathematically this kind of a thing is incorrect, as long as you get the correct units at the end, write down the correct units at the end, this is okay, okay? So that's also the convention that I'm going to use. It's a convention, right? So when I'm explaining something, and if I want to compute something, then at the intermediate steps, I'm going to forget about the units and write down the units only at the very end, all right? Just keep this in mind. I know that I'm making a mistake in here, but otherwise, it's going to take a long time to express everything, right? Next, I'm going to say something about the dimensions or the dimensional consistency of all equations. So all, let's say, physics formulas must be dimensionally consistent. For example, I think this is kind of interesting. So Einstein's equation, right? Everybody knows about this. So this is the energy. What energy? Probably this is some other concept that we have to study later. But right now, let's just forget about what that thing is. So in this semester, we are going to write down an expression for the kinetic energy, for example. This is 1/2 of mv squared. And I mean, we are also going to meet some other kinetic energy expressions like, I don't know. I mean, we are going to meet things like, let me write k in here again. It's like 2/3 of mv squared and things like that, okay? When we talk about the rotation of some disks and things like that. Rolling motion of the disks or something like that. For example, we can meet these kind of expressions. So what's common in all of these is that, well, on the left-hand side, we have a quantity with the dimensions of energy. meaning might be different. So that's what we call as rest energy. This is the kinetic energy of a single point particle, perhaps. This is the kinetic energy of a rolling disk or something like that. Yeah, whatever. Therefore, but they all have the same dimension, right? There are different quantities, but they are all energies. And on the right-hand side, I have the product of something with the dimensions of mass multiplied with something with the dimensions of the length squared, right? So sorry about this, velocity squared. So this is consistent with the fact that the energy, the dimension of the energy is equal to the product of the dimension of the mass multiplied with the length squared divided by time squared, okay? So all of these formulas are different formulas. They have different physical reasoning, but all of them should be consistent with this thing, okay? So this gives us an idea that perhaps there's some kind of another physical system where I need to express energy, and I need to express this energy in terms of some kind of a mass variable, some variable with the dimensions of mass, and some other variable with the dimensions of velocity. How the formula can look like, okay? And the answer is basically obvious because, I mean, this is the only way that I can combine these quantities. So there is no way that I can form a formula that contains the square of velocity and the square root of, square of the mass and the square root of velocity. So it's not possible that this would give us some kind of a quantity with the dimensions of mass, okay? So as a result, whatever the formula is, I mean, if I have some kind of a mass and some kind of a speed, and I have to relate it to some kind of an energy, then the formula should look like this. It is mass times velocity squared, and there's a constant in front. And this constant is just dimensionless, right? It can be a number like this, like 1/2 and 2/3, or I don't know, pi squared over 2, for example, or 1 over, I don't know, 92. It can be anything, actually, without deducing what the actual formula is. We cannot know what the coefficient is, right? So let's say it like this. We cannot know the value of that constant without actually deriving the formula. Without deriving the formula, we cannot know what that coefficient in here should be. It can be anything, but we know that it is dimensionless. But what we know is, without deriving the formula, this is something that we know. The right-hand side should contain mass with the first power, and it should contain the speed squared, right? Because otherwise, I cannot match the dimensions, right? So in an equation, the dimensions of the two sides should match with each other. We cannot have something with the dimension of energy can be equal to something with the dimension of, let's say, force, right? Because they have different units and whatever. I mean, we can use any kind of reasoning with that. Okay, if this is clear, then I can pass the other things. Okay, so there are a few rules in here in writing a formula. We can multiply things. For example, let's say it like this. Quantities with different dimensions can be multiplied, divided. And we also can take the powers and things like that. All right, so I can have like mass multiplied with the square of velocity. All right, so this is a law, right? It's like mass multiplied with the velocity squared. All right, that's a load. I can multiply quantities with different dimensions. That's okay. But what I cannot do is to add them, let's say, quantities with different dimensions cannot be added or subtracted. Okay, so as a result, I mean, things like, for example, 2 kilograms plus 3 meters. This is meaningless, right? I mean, in no part of physics we can meet this kind of an expression, right? I mean, try to think about it, right? I mean, basically, if you would like to think of the quantities, physical quantities as numbers, here we have an example of two numbers that I cannot add up because that operation has no meaning at all. All right. So as a result, this is something forbidden, right? I cannot add up two quantities with different dimensions. I can only add up two quantities with the same dimension. Only, let's say, quantities with the same dimension can be added up. Okay. Added or subtracted, all right? Subtraction is essentially an addition. Okay, so 2 kilograms, sorry, 2 kilograms plus 3 grams, that's okay. That's meaningful. I mean, we can give a meaning to that, so that's perfect. So let me actually do this red color thing so that this is understood completely. Okay, so this then gives us this idea in here. So think about functions like most, let me say, complicated functions. Like exponential, logarithm. I'm just writing these because these are the ones and that we meet a lot. So the trigonometric functions, etc. Let me just say it like this: the essential argument. So I'm going to talk about the exponential function. Everywhere without a unit is dimensionless. Every quantity without a unit is dimensionless. Yes. But some dimensionless quantities might have units, and the angle is a nice example for it. But I'm just going to perhaps say it in here, and later we are going to visit. So the exponential function, I think you are going to see this in calculus, but I'm just going to write it in here. So there's something called a Taylor series expansion. So this can be expanded like this. This is 1 plus x squared divided by 2. And then x cubed divided by 3 factorial and so on, and whatever. So there's this power series expansion in here. You can see that there are these things added up in here. So that means all of these things should have the same dimension. So x should have the same dimension as 1, and this should have the same dimensions as x squared and so on, right? All of these terms should have the same dimension, right? Which means x must be dimensionless. Okay, so that's the idea in here. So all of these functions, I mean, I can use this kind of an argument for all of these functions. So most complicated functions like the exponential function, the logarithm function, and the trigonometric functions, the argument must be dimensionless, right? There is no meaning of writing a dimension inside the arguments of these functions. So there's no meaning of the cosine of 1 kilogram, right? So let's say it like this: the logarithm of x, I don't know, the sine of x, for example, tangent of x or cosine of x. So all of these x's in here, right? X must be dimensionless. Okay, especially for the trigonometric functions. We are going to usually write angles as the arguments of the cosine and sine functions, right? Angle is a dimensionless quantity. So I'm going to come back to this later. But it has, let's say it like this, it can be expressed in different units. Okay, so for example, 90 degrees is the same thing as pi over 2 radians. We're going to talk about these units later, radian unit. There's actually one more unit that people use. I think it's called grad. In calculators, we always see this unit, but I have never seen it used. But in military, they use milliamps, for example, and things like that. There are other units that people actually use. But the quantity is actually dimensionless because it appears inside the argument of these trigonometric functions, right? But later we are going to see why it has to be considered dimensionless, because we are going to argue that the radian unit is actually defined in a dimensionless way. Okay. I don't know if you have any questions in here, but I mean, this is one common theme. So when you see an exponential or one of these functions, the argument should always be dimensionless. Just keep this in mind. There are other things like that. Sorry about this. I opened many different versions of calculator. I don't calculate anything. Okay, we don't have much time left. So usually, let's say it like this. If f of x is a polynomial with let's say at least 2 terms and dimensionless coefficients. Yeah, I'm saying, like, for example, let's say p of x is equal to 2x squared plus 5x cubed, right? Let's say it like this. I mean, there are at least 2 terms, but also the coefficients should also be dimensionless as well. In that case, so x must be dimensionless. Obviously, I mean, it's the same argument. So for most functions, actually, so the dimension of x squared should be the same as the dimension of x cubed. So therefore, from here, you can then deduce that the x must be dimensionless. Okay. In any case, for most functions, therefore, the arguments should be dimensionless. I mean, even for these kind of things like these kind of simple polynomials. But for the power function, let's say it like this: if p of x is a single power, like, for example, p of x is equal to, let's say, 3x to the 4, right? It's just the 4th power, for example, right? In that case, X may have a dimension. Right? That's just the only exception of functions that can accept the, I mean, if the function is a simple power, then the argument can have dimension. Otherwise, the argument should be dimensionless, okay? That's the essential idea, but I mean, don't try to think of it as some kind of a general rule. Sometimes we can write polynomials, but the polynomials might have some dimensionful coefficients. So there are these kind of possibilities as well. Okay, in any case, so as a result, by using these kind of rules, then you can somehow analyze analyze a formula. So I'm just going to write down a formula in here. It is unimportant. So that's the kinetic energy of a relativistic particle with mass m and speed v, right? So it's the kinetic energy. It appears that the formula is this. It's kind of a complicated formula, but I think when you take the special theory of relativity in physics 202, you're going to see this formula. It's the kinetic energy expression, but for a relativistic particle. So in that case, basically, K is expressed in terms of basically these three quantities, okay? Two of them are variables, mass and the speed. They depend on which particle you choose and at which speed it is moving, right? Speed of light, C is the speed of light in here. It's a constant, but it's a constant with a dimension. So as a result, in these kind of formulas, we can all, I mean, these constants enter into the formula as if they are a variable, so they appear inside the formula. And so as a result, inside the formula, we are going to have an expression that combines all of these, all right? So in any case, I mean, this is the correct formula in here, but you can check that this is actually dimensionally correct. So the first thing that we notice is that V over C ratio, this is dimensionless. If I have some kind of a dimensionless quantity, then I can evaluate any kind of a function of it. So as a result, for example, the 1 over the square root of 1 minus x squared, basically, right? Let's call it like this is f of x. I'm essentially computing the value of that function at that ratio. And basically, the argument of that function is dimensionless, has to be dimensionless. It is wrong. We can subtract 1 from the formula. We cannot subtract 1. Sorry about this. Yeah. Sorry. Thank you very much. It is dimensionally incorrect. Yeah, it's the MC square should be subtracted. Okay. Thank you very much. In any case, I mean, in this kind of an expression, therefore, we can evaluate, we can have some kind of a function of these dimensionless variables. So that's possible. But apart from that, this part is fixed. Okay, it's mass times velocity squared. So kinetic energy is basically can be expressed as mass times c squared and a function of this dimensionless variable. Right? So when we do dimensional analysis, we actually deduce this general form in here, right? So we know that somehow on the right-hand side, I should have a quantity with the dimensions of energy. So I just write down this quantity in here. That can be anything. So I could have written mass times v squared in here, mv squared as well. And then I just multiply it with any function of dimensionless variables, quantities that I constructed from the dependent variables. Independent variables, sorry about that. Okay. Sorry, sorry about this. Thank you for warning me. How V over C is dimensionless. I didn't get it. V has the dimensions of velocity, and C has the dimension of velocity as well, right? Here, I think I specified it in here. Kinetic energy of a relativistic particle with m is the mass and the v is the speed, and of course C enters in here as the speed of light. Speed of light. So the speed divided by the speed of light, it's the ratio of two speeds, so that's dimensionless. Okay, according to the some other part of relativity theory, that ratio should always be smaller than 1, for example. I can compare it with 1. Sorry, here f of x is 1 over this minus 1, all right? Sorry about that. So it appears that this is the correct expression in here that I need to insert. Okay, so that's essentially what dimensional analysis is. By looking at the dimensions, I can actually guess what the general formula might look like. You can basically say things like that, but by using dimensional analysis, you cannot say anything about what that function should be. Okay, so here it's a complicated function. So as a result, if on the right-hand side, if among the independent variables, you can construct a dimensionless quantity, then you cannot get what the formula is. But there are situations where on the right-hand side, we have, I mean, we cannot form any dimensionless ratios like that, for example. In this case, we can guess what the formula is, right? That's one example. I'm just going to write this thing down. So a car with cross-sectional area A is moving with speed v inside air with density rho. Let me say rho air, right? How much power must the car use in order to keep, to maintain the same speed? Okay, so this is a question like this. So we have a car in here. The car looks like a cylinder, right? I can model the car as a cylinder. So this cylinder has this cross-sectional area A. This car has a cross-sectional area A. It is moving with speed V, and there's air around it. The density of the air is rho. Okay, so because of that, there's air friction. So the air friction tries to slow the car down, but the car somehow uses energy to actually also to speed up in a way, but of course it only maintains that speed. So as a result, it is moving with constant speed now. How much power it should be using? Okay, so I'm going to solve this problem later, right? There is a way of actually deriving this formula by using physics. It's not a precise exact derivation, but I'm going to derive it later, right? When we see the energy concepts, we are going to solve this problem, okay? But at this point, we don't know anything about the physics. Well, we have some guesses actually. Usually we have some things like, I don't know, some quantities in here. So there's a dependent variable. That's basically the power that the car spends. I would like to express this in terms of the independent variables. Independent variables. Independent variables might be the actual variables that you can change, like the area of the car and the speed. So this is the cross-sectional area of the car, the speed, the density of the air. So perhaps you can do this inside an, I don't know, closed chamber where you can change the pressure of the air. So you can also change its density, for example. Why not? There are other quantities that you might also change, like, for example, there are the temperature of the air, for example, that might also be relevant somehow. The length of the car, so the car has a length, and there's the length in here. The mass of the car, right? I can also add all of these other quantities in here as well. I mean, there are too many variables that I can also count in here, but by using some simple analysis, perhaps I can eliminate some of them. So for example, mass of the car, probably this is not relevant. I mean, you might think that if there are too many passengers inside the car is going to spend too much energy, but usually this is the energy that's actually spent in order to increase the speed to that final value. To maintain that speed, you don't have to spend that much. I mean, the energy spent should not depend on the mass of the car. It only should depend on the force, the frictional force that the air applies on the car, but it shouldn't depend on the other properties of the car. Okay, so you can also eliminate things like, for example, the length, because we are going to see the process in here. So what happens in here is that when the car is moving, there are these air molecules in front of it. There are these air molecules in here, and the car pushes these air molecules in the sideways, right? So as a result, the cross-sectional area, the front area of the car is important. It's a very important quantity because it determines the amount of the air that should be pushed around. So therefore, this area is a variable that changes things. The density of the air, the mass of the air molecules, this is important. So that's also enters into the picture. The speed also enters into the picture because we know that if the speed is 0, the power should be 0. So speed somehow is relevant. We know that. But the others probably has less relevance. As a result, we just forget about them. I'm going to do this with the color red. We just forget about these, all right? So as a result, I'm going to take these as independent variables, right? Sometimes the independent variables might include some fundamental constants like speed of light, or I don't know, Newton's constant of gravity and things like that. In that case, we are also going to include them into in that list. If somehow I believe that they should also enter into the derivation, I need to do this. In any case, I'm just going to write down the things in here. So the power is basically the energy spent per unit time. So its dimension is mass times length squared divided by time cubed. Okay, so the area has the dimensions of length squared, and the speed has the dimensions of length divided by time. Right, let me write this thing down correctly. And what else? The density of the air has the dimensions of basically mass divided by length cubed. Okay, you can easily see that by combining these three quantities, the area, the speed, and the density, I cannot form any dimensionless quantity. So no dimensionless quantity can be formed. I cannot form any dimensionless quantity, which is great because that means that I cannot have these unknown functions like exponentials or logarithms inside the formula, right? That's great. So therefore, this means that by a suitable product of all of these, probably I can obtain a quantity with the dimensions of power, but there's only one way that I can do this. So the formula should actually look like this. So that power should be some kind of a constant, which is dimensionless, multiplied with some power of the area, some power of the velocity. So let me use K in here, and some power of the density. Right, so let me call this as S. Okay, so this constant is dimensionless. I cannot know what this thing is. I can only guess its value. Sorry about this. Let me complete this quickly. So I'm just going to write down the shortened forms in here. So that's mass times length squared divided by time cube. So now I write down the same equation in terms of the dimensions. So here on the right-hand side, I have some mass to the power something, length to the power something, and time to the power something. But let me carefully write all of them. Mass is coming from only the density. So this is mass to the power S. Length is coming from lots of different things. So let's just skip this for the moment. Time is coming from velocity. So therefore, this is minus K. And all right, so length is coming from the area. We have 2m from velocity plus K, and from the density, which is minus 3s. All right, so I think this is understandable. So what I do is I just match the power. So mass has a power which is 1, so therefore that's equal to S. Length has a power which is must be equal to 2n plus K minus 3s. And the time has a power of minus 3, which is equal to minus K. Okay. So from here, I can see that S is equal to 1, K is equal to 3, and I need to solve this. So 2 is equal to 2n plus 3 minus 3. Oh, yeah, that's nice. So therefore, n is equal to 1. Therefore, the formula should look like this. The power is constant multiplied with the area, the density of the air, multiplied with the cube of the velocity, cube of the speed. This is the formula then. I cannot know what the constant is, but later we are going to argue that this is about 1/2, right? We are going to see the reason behind this when we see the physics of this phenomenon here. But here, what we have achieved is significance, okay? Without knowing any physics, well, with knowing only a little bit of physics, because we have to eliminate things like the length of the car and the temperature and things like that, right? Without knowing any physics, we were able to derive a formula. This is actually a well-known formula that the power actually goes like with the cube of the speed. So that means if you double the speed of the car, then you are going to spend 8 times more power. So at high speeds, so therefore this becomes actually quite a significant dependence. So the engineers actually are faced with these kind of problems actually. In any case, that's something else. So as a result, this is a nice thing actually. I mean, there are lots of different places that you can use this to derive formulas. But what's important in here, I mean, this should actually give you an idea that when you derive a formula, sometimes you make a mistake and you just forget some of the constants and, I don't know, variables, powers, and things like that. You can use this dimensional analysis to check the dimensions, right? This is one of the things that all of you should be doing, right? This is very important. In the exams, for example, in the homeworks, you should actually get this habit of checking the dimensions all the time. So whenever I solve the problems in here, I will also be doing the same thing, right? Check the dimensions at the end because we are all human, we can make mistakes. I made a mistake, for example, up above. It was an important mistake that I could catch by checking the dimensions, right? So that's an important habit that every physicist should have. Okay, so that's why this is important. And that's why we have spent that much time on this. Okay. So let's stop the recording.